think it might be a little soft. Okay, so I sent a handout in the classroom, and I don't have like the problems on my whiteboard, so you might want to go open that if you haven't. But today I'm going to be talking about states, and I think they're very useful in lots of different problems, specifically in random walks and two-player combinatorial games. So a state is basically an intermediate stage that's part of a larger event. And I think you'll understand that more once we get to the examples. So I'll just start the first one now. So this one's relatively simple, but basically it's asking for the expected number of rolls of a first six-sided die until a 1 is rolled. So what we do is we let E be basically the answer, which is the expected number of rolls until a 1 shows up. And we think about this in terms of like what happens when we start. So because we're looking at rolling a 1, we roll a 1 with probability 1/6. So that's here, and that takes 1 roll. And then probability 5/6 is rolling something other than a 1. So that also takes 1 roll. But after that, again, which means that we need another E rolls. If you have questions, just ask. But this translates to equals 1/6 times 1 plus E. And then this gives us E equals, 5/6 E equals sorry, equals 1/6E, so equals 6. And this makes sense because a 1 is rolled with probability 1/6, and it takes an average of 6 out of 1. So in this problem, there's pretty much only one state, which is the one that we start at. Most problems are not going to only have one state. This was just for a simple example. So the next one is, I'm going to erase. The next one is about a two-player game. I took it flute because I thought it was a nice example. There's two people called R and G, and they're playing a game with 2021 stones. So, and each person picks a divisor of the number of stones currently in the pile and removes that many. So R goes, and then G goes, and then R goes. And doing that player has a winning strategy and also find out what that strategy is. So 2021 isn't extremely important. So we can just kind of look at some smaller examples first, starting with 1, 2, 3, in terms of what are called winning and losing positions. So a winning position is one in which a player is able to make the most of them to win. That sounds kind of obvious, but losing position is one where every move that you make, like, it has to make you lose. So you're basically guaranteed to lose if you're at a losing position, given that everyone plays optimally. So in other words, then has to have at least one move that makes the opponent go to a losing position, and a losing position, all of its moves go to a winning position for the opponent. Okay, so I'm not really going to explain this. It's on the handout. If you really 2, 3, and 4 are losing, winning, losing, and winning. I can explain one. Like the first person, they have to take this one and then they lose. And 2, 3, and 4 are pretty similar. And yeah. So this creates a pattern, and we claim that an even number of stones in the pile is a winning position and an odd number is a losing position. So sometimes these problems are able to be proved is by strong induction. So the base case is n equals 1. We've already said it's a losing position, so that satisfies the claim. And for the inductive step, if we assume that for all numbers from 1 to n, if it's even, then it's for all numbers 1 through n, basically, it satisfies the claim. Then n plus 1 all claim. So if n plus 1 is even, right, then n is odd. And subtract 1 from the number of stones in the pile and get to n stones, which by the inductive hypothesis is odd and losing for the opponent. So then n plus 1 stones is a winning position. And if n plus 1 is odd, then n is even. If n plus 1 is odd, all of the divisors of n plus 1 are odd too. So then you're going to subtract an odd number from an odd number. So which is a winning position for the opponent. So basically a losing position if n plus 1 is odd. Does anyone have any questions so far? Okay. I'm going to assume everyone gets it. So okay. Okay, so we've shown that even numbers of stones are winning and odds are losing. And since we're asked about 2021, right? 2021 is odd. So that means it's a lose. And that means that the first player who's presented with 2021 stones lose. So the second player, who is G, having strategy, and the strategy is literally just this proof here. So by subtracting 1 every time it gets an even number, which is all the time, it forces R to get an odd number every time, and then it keeps going. So G is going to win that way. Okay. We're doing better on time than I thought, but okay. So now let's do the first problem. So it's about an ant that's moving around on a tetrahedron. So here, A, B, C, D. And the ant is on the ant walks to an adjacent vertex randomly. I didn't put that in the handout, sorry about that. But yeah, and then it's a possibility that the ant is back at A after 4 minutes. So we're talking about like A tetrahedron. So I think the motivation for this is like just looking at B, C, and D with respect to A. And you find that since it's a tetrahedron, B, C, and D are all symmetric with respect to A. So you can kind of split the ant locations, and either it's on A or it's not on A. So if it's on A, then, oh, this is called a state diagram. Basically, you show like what happens between different states. If it's on A, then with probability 1, it has to go to B, C, or D, which is not on A. If it's not on A at some point, then it goes to A equal to 1/3 because, for example, B has 3 choices and one of them is A. And then this gives us 2/3 for going from a going to another one of B, C, or D, if that makes sense. So yeah, if you look at this diagram, you don't really have to draw it, but I think it's helpful sometimes for like more complicated problems to just visually see like what happens between different states. But we're going to create variables that the ant is on A or not on A. So we say AN and BN are the probability that after n minutes, the ant is on A and not on respectively. So all of this gets copied over. Okay, yeah, so given this, we're asking for what A4 is equal to. And we're going to start using this. Basically, AN, you can get to A by being not on A in the previous minute, if that makes sense. So if you're not on A in the previous minute, that means, and you go to A with probability 1/3. So that's going to be AN equals 1/3 BN minus 1. And then for BN, it's similar. If you're on A in the previous minute, then you multiply by 1. And then if you're not on A in the previous minute, it's 2/3 times BN minus 1. And then also, any given minute, obviously the ant is either on A or not on A. So we have AN plus BN equals. So after this, it's just arithmetic. And I guess we can do it. I don't really you can like make a table. N equals 0, 1, 2, 3, 4. Okay. So at the beginning, 0 is the probability that after 0 minutes the ant is on A, and that's 1 because you already know it's on A. And similarly, B0 is 0. And then you can start using these formulas here. So A1 is equal to 1/3 of B0, which is 0, and 1 is equal to 1 plus 0, which is 1. Okay, this is equal to 1/3 and plus 1. So 0 plus 2/3 is 2/3. And then A3 is 2/9. B3 is 1/3 plus 2/3 times 2/3, which is 7/9, I think. And then A4, which is what we're asked for, is 7/27. I hope that's right. I don't remember the answer, but yeah. It's just arithmetic. Okay, does anyone have any questions about this problem? Okay, so I'm going to erase that. Okay, so the next problem is yeah, a lot of people thought this problem was misplaced, and also a lot of them liked it. So I don't really know, but it's basically just that you have a dodecagon, so 12 vertices, and there's 3 frogs. In the beginning, they're at A4. Well, I'm not going to write the A's, but you get the idea. They're at A4, A8, and A12. So each minute, the frogs jump to adjacent vertices randomly and independently. So they stop when they arrive at the same vertex, and they're asking for the expected number of minutes until they all stop jumping, which means 2 of them have gotten to the same place. So for this problem, slightly different what the states are, but I think if you've seen like problems about where things are on a circle, it won't be too hard to figure out. Does anyone want to say what the states can be quantified as? No. Okay. So we can describe the states with like the number of gaps between the different frogs. So that means like between 12 and 40 points, and then 4 and 8, there's 3 points, and 8 and 12, there's 3 points. So we let E, A, B, C number of minutes until it ends if the frogs are A, B, and C apart. And A plus B plus C is weighs 9 because there's 12 points total and 3 frogs. So 12 minus 3 is 9. And we're asked for E333 because that's where they are initially. So The way you find the relationship between different states is not really hard. It's kind of just listing out or finding all the possibilities. So I'm only going to do one of them. The other ones are all pretty similar, so I'm just going to write them down later. Yeah, for the sake of not taking too much time on stuff that's not that interesting. So E333, if we take one minute, then we're going to get to some other states with certain probabilities, if that makes sense. Similar to the very first example. So I'm to assume that, why are there so many chats? Okay, I'm going to assume that 12 will go to 11, and then if the one at 12 goes to 1, then it's just symmetric. So later we're going to multiply by 2. So 2 times something. Okay, so if the one at 12 goes to the one at 12 goes to 11, then the frog at 8 can go to, let's say, 7. And then the frog at 4, if it goes to 3, right, then we'll get what, 3 again, 1/8 probability. And if it goes instead to 5, then we get E135, right? Because there's between 5 and 7, there's 1, and then between 5 and 11, there's 5, and 7 and 11 is 3. So 135. Oops. Okay. And so that finish off when 8 goes to 7, then yeah, if 8 goes to 9, then the gap between 9 and 11 is 1. So to have a 1, and then if 4 goes to 5 or 4 goes to 3, either way we get 135. So that would be plus 2/8 of 135, which is 3/8 total. So that means that, remember we multiplied by 2. If 12 goes to 1, and this is plus 1/4 E333 plus 3/4 E135. Okay, and this means that you move this here. We have E333 is 4/3 plus 5. Okay, so now we have a 135 here, and you basically just do the same thing, looking at the different pubs that it can go to. So I'm not going to actually go through all of it because it will take a while, but we have 1 plus 1/8 E117. So that means there's 1 gaps of 1, 1, and 7, and then half probability that it stays as a 135, and half probability that it goes to 333. That 1/8, 1/2, and 1/8, they add up to 3/4. So that means that 1/4 of 1/4 that the game, the frogs all just stop because the ones that are one apart both move to the same thing. Like if they go like this, probably that this happens, and that's just 1/4 times 0. Okay, and in terms of 1, 3, 5, just on one side, plus, whoops, it's taking a lot of space. 1/4 times E117 plus 1/4 E333. The final one, I was going to go directly to the isolated term. It's a little bit similar to E333, but not exactly. That equals 4/3 plus 1/3 E135. So now you want to solve for E333, but I think the easiest way to do this is by plugging in this equation and this equation to the one for E135, because they're only in terms of E135. So then you can solve for E135 and then just get E333 from the first equation. So we can do this 2 plus 1/4 times 4/3 plus 1/3 E135 plus 1/4 times plus E135. And this comes out to be 2 plus 1/3 plus 1/12 E135, third plus 1/4 E135. Oh, that's not that nice. I will. So that is 2/3, so 8/3 plus 1/3 E135. I hope that's right. And remember this was 5, so you get that E135 is 4. Yes. And then we just plug that into plus 4 is equal to 16/3, and the answer is 0.19. Any questions? All right. So now I think the last two are just about 2-player games. So this one. So there's 2 players and they alternately take turns drawing matches from this pile of matches. Yeah, so there's N1, 2, all the way up to the floor of square root n matches. And the person who takes the last match wins. And we want to prove that if the pile initially contains a perfect square number of matches, then the first player has a winning strategy. Okay, so let's say that at the beginning there's m² matches. Right, so then the player can draw up to m matches, so it will become m² minus 1 to m squared minus m. And first, we're trying to show that the first player has a winning strategy, meaning that they can get to a losing position eventually. No, they can get the opponent to a losing position or get themselves to a winning position eventually. So if we first assume that m squared minus m through m squared minus 2 if there is a losing or there exists a losing position in this like interval, that means that the first player can just remove however many matches to get to losing one, and then they'll force the second player into a losing position, and then they'll win. So this case works. If there is no losing position, meaning that all of them are winning positions, then the first player can just take one match, their first turn, and then that leaves the second player with m squared minus 1. And what this does is now the floor of m squared minus 1 is m, right? So the second player can get to m squared minus 2, m squared minus 3, all the way down to m squared minus 1 minus in parentheses m minus 1, which is just m squared minus m. So this is good because we already assumed something about this. And what we assumed is that all of them are winning, right? So no matter which one of these that the second player gives to the first player, we're going to be presented with a winning position, which means that the first player then gets a winning strategy. Okay. Apparently, there are 3 minutes left. So I will, I guess, outline the last problem. It's not too bad. So diagonals of a regular 2n-gon. So basically, it has an even number of sides. And given that, like when you draw diagonals, they can't intersect, and the player who can't move loses, it's asking which player has a winning strategy and what is that strategy. So just for an example, let's take a hexagon. Yeah, so the key idea that is that this is about symmetry, and there's a lot of problems with two-player games that like rely on symmetry. So the first player has a winning strategy because I think any like diagonal that cuts the 2n-gon into like exactly half, like two congruent circle, like this would be the diameter, is what I'm trying to say. If the first player just takes this diagonal on their first move, then whatever the second player does, they can mirror it in the other side of the polygon. So like they reflect this across the diameter to this. And you know that those won't intersect because it's a reflection. So yeah, that's the strategy. And that's the end. Thanks for listening.
Okay, so thank you, Catherine Lee. And so thank you everyone for coming. And next week will basically be the same, but the guest lecturer will be Esther. Thank you for coming.